In this video, I'm going to show you how to use the substitution rule to find the antiderivative of some complicated integrals. Now, dy and dx that appear in the derivative dy dx are called differentials. dy dx equal to f prime of x is said to be in derivative form. And then if I multiply both sides by dx, I get dy equals f prime of x times dx, which is in differential form. And this form is what we're going to be using when we use the substitution rule. Now, this technique can often be used to convert a complicated integral into a simpler one, which we then can integrate. So let's say that we start with an integral, f of x dx, and we're going to let u equal to some convenient x stuff. I know that's informal, but let's say it's some x stuff that's already in the integral. And we're going to say that u is equal to g of x, which is a part of the integrand. Then, to complete the substitution, we must also substitute for dx. So to do this, we're going to find that du dx is equal to g prime of x, which is the derivative from this part here. We're going to multiply both sides by dx, so we get du equals to g prime of x dx. And then we're going to divide both sides by g prime to get dx equals to du g prime of x. Then what we have is f of g of x times g prime of x dx is equal to the integral. So all of this right here actually, we'll do this part first. So this part here is equal to u, and then this part here is equal to du. Now you might be wondering where we got this f of g of x times g prime of x in the first place. But let's say that we were taking the integral of f of g of x. So we have to apply the chain rule. So remember, first we would say to find the derivative of f. So that would be f, and we use a capital, f of g of x. And then we find the derivative of g of x, which is then g prime of x. So that's how we get this part here. Actually, I probably shouldn't be using capital F, since usually we think of capital F as the antiderivative. So I'm just going to say f prime. And however, what I've done here is I've just written it as f because we're going to find the integral of that. So we can just consider it as f. Now, let's say that we want to compute this integral here. And it's quite complicated because we have a power of 30, and it's not something that we want to multiply out 30 times. So we're going to let u equal to x squared plus 1. Then du is equal to 2x dx. And now we have that du divided by 2x equals to dx. So we're going to substitute this, and u is equal to x squared plus 1, so we have u to the power of 30. And we have the 2x, and we now know that also that dx is equal to du over to 2x. And this cancels off. Now you actually don't have to do this step here if you want to, because from here I can see that du is equal to 2x dx, which is actually this term and the dx combined together. So those together is equal to du. So you can actually go straight to u to the power of 30 du. Okay, and then integrating, we get u to the power of 31 over 31 plus c. And then we're going to substitute the u of x squared plus 1 back into u. So we get x squared plus 1 all to the power of 31 divided by 31 and then plus c. So to use substitution, you need to choose an expression for u such that when you substitute the u and the du into the integrand, there is not going to be any x remaining. So you notice here that I canceled off the x's. Now if it doesn't work, then you should try a different u substitution. Often there might be different expressions, so you might want to try a different expression to see if you can get rid of the x's. So the steps for integrating is first make a choice for u. Say u equals g of x. We're going to compute the derivative du dx equals g prime of x. We're going to make the substitution for u and for du. And then after you've done that, make sure that there are no x's remain, because if there are x's, then you've made the incorrect substitution. And then you're going to evaluate the resulting integral if possible. And then at the end, make sure to replace all the u's by g of x, so the final answer is in terms of x, since our question originally started with x. All right, so let's take a look at some examples. So here we have the integral of dx plus 7 to the power 4. We really only have one choice for u, so we're going to let u equal to 10x plus 7. So du is equal to 10 dx, and then du divided by 10 equals dx. Now we're going to substitute everything that we have here in the right side into the integral. So we have the integral of u to the power 4, and then the dx is du divided by 10. Now what I can do is pull out that 10 to be 1/10 in the front, and that will be the integral of u to the 4 du. So that gives me 1/10 times u to the 5th over 5, and then plus c when I integrate. And then u, I'm going to now substitute it back in with 10x plus 7, all to the power 5. And then I can multiply my 10 and 5 in the denominator to give me 50. And then I have plus c. All right, let's try a different one with a base of e. So we have an exponent of 3x plus 5. So that seems like the complicated part there. So I'm going to let u equal that binomial. Du is then 3 times dx. And then du divided by 3 equals to dx. So let's do the substitution. I have the integral of e is still there, but it's e to the power of u times du divided by 3. I can pull out the 3 from the denominator and put that as 1/3 in the front, and then the integral of e to the u du. Now I know it's kind of weird that sometimes I have it as times and sometimes I don't write it down. So remember that du or dx, whatever it is, remember that was the width of those rectangles. And now that we're writing it as an integral, we're saying that those rectangles are tending to be a width of 0. So now we have 1/3, and the integral of e to the u is still e to the u, and then plus c. Substitute my u back in here. I get e to the power of 3x plus 5, and then plus c. All right, let's take a look at this one, because we have a fraction, and I'd like to show you some different types of examples. And we're going to let u equal to the 4x plus 7, which is in the denominator. And then we have du equals 4 dx, and then du divided by 4 is equal to dx. Substituting all the expressions that we can, we get 9 divided by u, and then dx is du divided by 4. So I'm going to factor out the 9 and the 4 to put into the front. I'm not really factoring, I guess I'm just rewriting it with it as a coefficient in the front. So I have 9/4, and then 1 divided by u du. And if you recall, the integral of 1 over u is the natural log. So we have the natural log of the absolute value of u plus c. And then substituting u back in, I get 9/4 natural log of 4x plus 7. And then plus c. Excuse me. All right, so one more here. Let's say, because now I have 2 x's, and I want to show you what happens in this question here. So we're going to let u equal 4x squared plus 7. And now I have du is equal to 8x dx. So this time what I'm going to do is I'm only going to divide by 8. So I have the x and the dx left. You can divide it by 8x if you like, and then the x's you can see here will cross off. I kind of like to leave it. And so that I know that when I have x and dx, these two parts here combine together to give me du divided by 8. So I have u to the power of 4, and then I have du divided by 8. So this gives me 1/8, and then the integral of u to the 4 du. Now I can integrate u to the 4, so this will be u to the 5 divided by 5, and then plus c, and then u is 4x squared plus 7, so let's substitute that back in. And all of this will be divided by 40, and then plus c. Now notice that in this last example here, the x's canceled off, because I have the extra x. So we only had u's. Now if the x's had failed to cancel, we wouldn't have been able to complete the substitution, because when we integrate, and this says with respect to u, I should only have u in the integral. If I do have x's, that means that I haven't done the correct substitution. Now, what makes the x's cancel out? So it's the fact that I got the x from when I found the derivative of 4x squared plus 7. So this kind of leads to the following rule of thumb. You want to substitute for something whose derivative is also there. So let's take a look at two more examples here that are a little bit more complicated. So here we have a 3x squared plus 4, but I also have an x cubed plus 4x minus 5 that I can choose. Now, if you notice, if I take the derivative of the denominator without the radical, I'll get my numerator. So I'm going to let u equal to x cubed plus 4x minus 5, and then my du is equal to 3x squared plus 4 dx. So it's so convenient that it happens to be the same thing as this. So then I have the integral of 1 over root u, and then this whole part that I've circled is now going to be du. So integrating, or before maybe I'll make this as a -1/2 to make it visually easier. So I'm going to add 1, so I'm going to get u to the 1/2 over 1/2 plus c, and then substituting the u back in, I get 2, and the square root of x cubed plus 4x minus 5, and then plus c. All right, the last one here is a little bit weird because I have two functions that I could use, but we tend to take the higher one, so when I find the derivative, it will give me kind of the other one. So I'm going to let u equal sine and then 5x. So du is equal to cos 5x, but don't forget the chain rule, so it's going to be times by 5 dx. So I notice that cos 5x dx is right here. So what I'm going to do is divide by 5. So I'm left with that piece, this expression here. So this gives me the integral, and sine 5x is going to be u to the power 7. And then this whole part that I've circled is now going to be du divided by 5. So I have 1/5 integral of u to the 7 times du. So I have 1/5 times u to the power of 8 divided by 8, and then plus c. And then substituting this back in, I get sine to the power of 8, 5x, all divided by 40, and then plus c. So that's how you integrate using the substitution rule.